square.
Yeah, it's gone to a square and the timer's sticking up. Okay, I'm going to restart this timer. Cool, so, hello, I'm Gergo. I'm talking about ray tracing. There's a lot to cover. I've had to skip over a lot of things and I'll talk very fast and there'll be a lot of information on slides that I don't actually talk about. So let me know if you want to get the slides so you read through it or just have a look at the annotated bibliography. Things I'll cover is theory, maths, implementation, architecture and future initiatives. I'll talk about a bunch of alternatives as well to the base papers that I used. So first of all, what is CUDA? Is a parallel computing platform API, which essentially allows us to run code on the GPU in parallel. So in theory, it's a lot faster. This is kind of what it looks like. Any function that's annotated with the global annotation is a CUDA kernel. So this function will run on a GPU core, and this is how you launch it. You need to define the block size and the thread size. So why did I use CUDA? Parallelizing code is massively optimum when you've got a large degree of data parallelism. Obviously, it's dictated by Amdahl's law, so the percentage of code that can be parallelized over all the code. Ray tracing, we've got a lot of different pixels that shouldn't affect each other, so this is a prime target for a massively parallel application, which is why I did it on the GPU and using CUDA. So why is ray tracing good? Traditionally, we used local illumination, which only took into consideration the relationship between a single object and a single light source. Using ray tracing, we should take into consideration all light sources and all objects, so we don't need to rely on additional techniques such as reflection and ambience to get a realistic looking scene rendered. So what is ray tracing? Essentially, it's a box camera model. So if we think about this as the screen, and the pixels on the screen will shoot out a bunch of rays, and we see what they hit, and then we essentially collect all the information on the surfaces that the rays hit. What are rays? We have lines. Lines are infinite in both directions. On the opposite end, we've got line segments which have a start and an end point. So these are finite segments. Rays lie somewhere in the middle where we've got a start point, but they can extend into infinity, but only in one direction. They are defined in parametric form as any point on the ray at parameter t can be defined as the origin plus t times the unit direction. In theory, t can be extended beyond 0 into the negatives, but by definition, this should not be allowed. This is what it looks like. Start point, unit direction, we've got the t value, so you can move the point on the ray back and forth. This is kind of what it looks like in code, standard C++, and we've got CUDA. Anything that's annotated with device, this will only run on the GPU. And then here's the formula, origin plus t times direction. How do we calculate intersection? It depends on what object we are trying to intersect. And different shapes have different methods for checking intersection. Starting with the sphere, the Cartesian equation is x squared plus y squared plus z squared equals r squared. For a sphere, if we want it, this is about the origin. If we want it about an arbitrary point, then we need to define the point in the equation. In vector form, we can define any point on the ray to be, and any point on the sphere is essentially the center minus the point. So if we plug this into the equation, then we've got center minus points, dot product center minus points, which gets us the radius squared. Taking the dot product is essentially just the distance squared. So if we take a vector from the center point to the origin and we square its distance, then we get the radius squared. So that's that sphere definition. For sphere intersection, if we plug a point on the ray at parameter t into the equation, and then this equals radius squared, any point which satisfies this equation at a point on the ray at parameter t, this will give us an intersection. So when we expand it, we get a nice quadratic equation, and the only unknown is t squared. So what do we do with this t squared? We see how many roots it has. If it has 0 roots, we fully miss the sphere. With 1 root, we are tangent to the sphere, and if we get 2 roots, then we went through the sphere. And we do this essentially by checking if t is less than 0. Anything less than 0 can't have a square root as the real number, and we don't care about imaginary numbers. So essentially in the intersection check, if it's less than 0, it's got no roots, so we return false. What about cuboids? So cuboids can be defined by a minimum and maximum point. Anything between these 2 points in space will be part of the sphere. And we can use these min and max points to define slabs about each axis. A slab is essentially two parallel planes. The distance between these parallel planes is finite, but they extend infinitely in the other two axes. So taking, for example, the X slab, there's a finite distance between these planes, and the planes lay on in the YZ axis. So essentially, a ray intersects the slab as long as it's not parallel to the planes of the slab. Yes. So if the ray is parallel to the planes of the slab, we are either fully contained within the slab or we fully miss the slab. In my code, what I did was if the ray lies exactly in the planes, then it's calculated as a miss. We want to be within. And the ray intersects the cuboid if some part of the ray is within all three slabs at the same time. And we check this by calculating the t-values for the intersection points of the slab using these equations. So Tx min will be the x min. This is the x planes on the x slab's minimum x value, minus the ox, always the origin, and d again is the direction. So this will give us a minimum and maximum value for t where the ray intersected the slab, and we just do the same for y and z. An intersection will occur when all the minimum t values are smaller than all the maximum t values, as we see in this diagram. So we've got two slabs. This is in two dimensions to make it easier to visualize. So we've got a min and a min. This is where it intersected one slab. This is where it intersected another slab. These two mins are clearly smaller than the t values for the max. So this is an intersection with the cuboid. In this one, we've got a min and a max, and then a min and a max. So this t max value is smaller than this t min value. So this missed the cuboid. That's not an intersection. This is what it looks like in code. It's a lot longer function. This is just sort of the key parts of it. So first, we are doing a division by r directions. If r direction is 0, we need to handle it differently, so we're not getting divisions by 0 and funny results. And then we check if it's within it. If it is, or because equals, if it lays on the planes of the slab, then we are taking false. Else, we calculate the t-values. Depending on which way the ray came, it could come backwards, so we might need to switch them in at max values. Essentially, we set the section of the ray that intersects all slabs at this current point. And if, again, a min value is greater than a max value, then it is a miss, as we saw it in the previous slide. These are the two I implemented. I also looked into alternatives, so we can ray trace any shape, any polygonal shape, if we can check for ray triangle intersections. These are defined by three vertices, A, B, and C. So we've got a point which is defined as alpha A, beta B, gamma C, which we can expand into this parametric equation and then put it in matrix form. We can solve this equation using Cramer's rule. And in that way, we can check for ray triangle intersection, at which point we can check for any object that's made up of triangles. Let's talk about shading a little bit. Now we've got intersection, we can calculate normals, reflections, and materials. Now, different materials have different surface properties which dictate their behavior. At this point, there's an architectural choice to be made in code about the composition, the association. So we can use composition where we hard code these material parameters into the objects, or we can have separate material objects which are connected to the renderable objects. This is what it would look like. So if we've got a composition sphere, we would put the material parameters into the class. Aggregation, we've got a separate class, and then we just connect it to the actual drawable object. Now, what I went and did was a polymorphic implementation, so every drawable object only needs a single material pointer, which is in the code, it will be a derived class of the material, so we only need to worry about one pointer for every material, which gives us great control. And I think I talk about, because I did it this way because it gives me more control of the materials which I can then reuse. I also did save some memory because I've got a lot of objects and less materials. Using composition could be useful for procedural objects, and it gives you more control of it, how each object will look as opposed to each material that is applied to the objects. We've seen the implementation, talked about polymorphic implementation, and this is what it looks like in code. So we've got a base material class that implements a virtual function called scatter that is overwritten for each individual material. Because they've got different physical properties, scattering of the rays will happen differently. And in this case, every object will just have a material pointer that will point to one of these derived classes. Why is it useful? Again, a lot of control, so I can allocate memory for a number of different types of materials that I want in my scene, and then in these I can just put materials that I specify in this CUDA kernel. It gives me great control, gives me a range of materials that I can reuse for different objects. I'm going to cover dielectric materials because these are the more complex ones. Lamberts are straightforward. Upon intersection, a new ray will be created in a unit sphere that is tangent to the intersection point to the object, so they'll scatter in all different directions. Metal essentially just reflects the ray. That is also pretty straightforward. We can add a bit of fuzz to it to make it less reflective, but these are relatively simple shapes. What I'm going to talk about is dielectrics, where the ray will refract in some cases and reflect in other cases. Talking about refraction, refraction essentially changes the ray's direction when it travels between two different mediums with different refractive indices. So essentially the refractive index is 8 to 1 and 8 to 2, and then we've got the angles to the normal. As we can see, this one travels into a lighter object, one with a smaller refractive index, so it bends away from the normal. And a high refractive index would bend towards the normal. Essentially, the ray slows down, so it bends towards the normal. If it speeds up, because it's a lower refractive index, it bends away from the normal. So this is the equation to calculate it. You can expand it into this, and then essentially, the way we calculate a refracted ray is we take we calculate separately the perpendicular component and the parallel component of the refracted ray, which have been very helpful at putting into one equation. Essentially, this is the perpendicular component, and this is the parallel component. If you're keen-eyed, you notice that this part and this part is the exact same. That is because the parallel component uses the magnitude of the perpendicular component. I just put it in all in one equation. So we've got the refractive indices, 8 to 1 and 8 to 2. We've got the original ray, and we've got the normal. What we don't have is cos omega, which we can get by taking the dot product of the inverse ray and the normal to get cos omega. And that will allow us to calculate this equation. Now, in some cases, the rays will bend so much that they can't bend anymore physically, in which case we have total internal reflection. This is calculated using Fresnel equations in the real world. We don't need to worry about so much because we have an approximation we can use that is a lot less computationally expensive and a lot faster, and it still gives us pretty accurate results. Called the Schlick approximation, in which case the rays will be reflected instead of refracted. This is what it looks like in standard C++. This is what it looks like in regular C++. Again, we calculate in the parallel and the perpendicular components of the vector, and then we add them together to get the refracted ray. These are the overall alternatives that are implemented. So we've got the Lambert, the dielectric, and then the metal. There are other alternative material types. So we've got the diffuse. This is slightly different how I implemented it. This is a sphere constructed with origin at the intersection. What I've got is a sphere tangent to the intersection point. We've got dielectrics, we've got the metals, and we also have this one because we can add a bit of fuzz to it to make it less reflective. Then we've got other material types such as the plastic material. I think this is to do with subsurface scattering, and we can do the same. These fuzzy dielectrics would be trivial to implement. We just need to add a bit of fuzz. This one we technically have. We usually need to define a cuboid that is very thin. So these are some alternative material types. And here's the annotated bibliography. I wanted to show all the different materials I've got working with all the different objects. So we've got spheres and cubes. Spheres, metal, dielectric, and Lambert. Then we've got cubes here, cuboids, which are Lambert. The floor is a massive plane, it's a cuboid, and that's metal. And then I've got like a really thin dielectric cuboid bar going across on it. I wanted to make it look nice, so this is what I came up with. Future initiatives would be making the intersection calculations faster, optimizing it. Spatial partitioning, if arrays go in one direction, we don't really care about what's going on the other side of the world. We can organize objects using trees, up trees, so we again improve the intersection calculation speed, so we're not calculating for objects which are nowhere near that we need. I think that's it. Any questions?
Any questions for me? So you talked about the plastics as an alternative approach to the information subsurface scattering. What's happening there exactly?
Let me just go back to the diagram. So essentially the ray travels, it penetrates the object slightly, it bounces around between the atoms, and then it might find its way out. So what it will do is it will penetrate the material, bounce around a little bit, and some rays will find their way back out of the material, and they will again be scattered into air.
So it's modeled out effectively not modeling second interior intersection somehow.
Yeah. So implementing it, we could define another plane inside the plane, or we could define perhaps a distance, which is the maximum it can travel into. There are different ways to do it, but essentially this will have more illumination because instead of all the light being absorbed, that is absorbed by regular plastic, some of it will make its way back out and scatter all over the place.
You do it yourself using a kind of random probability that you merge again. Would that work? So rather than just having a fixed plane, you could have a probability that at a certain depth bounces back.
Potentially, I suppose the further it travels into the material, the less probable it is that it will find its way back out. It's more likely to be absorbed by the material.
What's the performance look like for your application?
So as I said, this video is 150 frames, 50 bounces per ray, 100 samples per pixel. This took, initially I thought it was going to take about an hour and a half to render. I did start playing some games while it was rendering, so it was closer to 2 hours. But 150 frames at that resolution is pretty decent. From some initial calculations I had, this is roughly 2,000 times faster than using just sequential execution on the CPU. So it's a lot faster than it could have been, but it's still kind of slow, which is why we need those future initiative optimizations that I talked about. Any other questions? No? Lovely.